Welcome back to the channel. It's the Earth Science Classroom. This video is on seismology and earthquakes, and we're looking at what is a megathrust earthquake. This is the Earth Science Classroom. Welcome back to the channel. This video we're going to discuss megathrust earthquakes. First, we're going to look at what a fault is in tectonics and seismology, then discuss what kind of fault or type of fault a megathrust earthquake is associated with and its characteristics, then look at where geographically these megathrust earthquakes occur on our planet and why they are historically and potentially one of the most fearsome natural disasters that we have on Earth. A megathrust earthquake occurs along a certain type of fault. Now let's discuss what a fault is. It begins with the crust and lithosphere and the stress and energy applied within this rock layers from the convection currents in the asthenosphere, which results in plate tectonic movement of the above lithospheric plates and, of course, crustal deformation. And this stress is going to cause strain and deformation within the rock, both elastic deformation, ductile deformation, and the more important, brittle deformation, which is going to cause the rock to go above its strain limit with the stress and break. This break is called a fracture or a rupture. Now, if there's still movement either side of this newly formed fracture or rupture caused by the continued stress, either compressional stress, which is going towards, tensional stress going away, or the opposite direction, which is shearing stress, then we call this a fault line. Now, there are two types of faults. There is strike slip, which occurs with shearing stress with a vertical fault line or rupture or fracture, and a dip slip fault. Dip refers to the angle, and the slip on both types refers to displacement and the movement of one side of the fault line. Now, in terms of dip slip, the angle is going to be diagonal across the rock, and it's going to fluctuate and change, and the movement of the hanging wall, whether it be down or up, is going to create different types of faults. Now, a normal dip slip is where the tensional stress is going to pull apart and the hanging wall will fall down. And the opposite, a reverse dip slip fault, is where you have compressional stress pushing towards along the fault line and pushing the hanging wall up vertical, which is what we're going to discuss today. Now, a megathrust earthquake is a special kind of reverse dip slip called a thrust fault. The thrust means the speed in which the hanging wall is moving and displacement occurs. Now, the fault line has a certain angle. It has to be less than 45 degrees to be classified as a thrust fault, but the average angle of the reverse dip slip in terms of a thrust fault is around 30 degrees. This means that the hanging wall, it can move quickly and explode up when the compressional stress is applied to this type of fault. Our current understanding of megathrust earthquakes, they occur along thrust faults and operate within the elastic rebound theory, which is our current understanding of how earthquakes operate, including the foreshock, main shock, and aftershocks, and the buildup of stress and strain within the rock along the fault line, and a battle between stress, strain, deformation, and friction between the two parts of the fault, the hanging wall and the footwall, in this case with the dip angle being around 30 degrees and definitely less than 45 degrees, and the sudden rupture, the sudden release, the sudden displacement where the stress overpowers the friction and the hanging wall is thrust forwards, thrust upwards in a diagonal vertical direction and releasing the energy concurrently to cause the earthquake. And this theory was devised by Reed in 1906 after the Great San Francisco earthquake in California. So now we know what a thrust fault is in regards to a reverse dip slip fault with a certain angle of the fracture or fault line. And if we take this into a real life situation, we're going to look at convergent plate boundaries where two plates are converging or colliding, and we have a difference in density between the two tectonic plates based on its geology, its thickness, and its composition. And we're going to have subduction, this zone of subduction where the heavier, denser plate colliding is going to be forced under through various forces and mechanisms, including the convection currents, gravity, and slab pull, under the less dense or more buoyant plate, and create a subduction zone at a certain angle, which would denote thrust. And this subduction will be where the stick and slip dynamics and the failure and the corresponding displacement and rupture would occur along this subduction zone, along the point of surface contact and friction between the subducting plate and the overriding plate in terms of the less dense one, which is more buoyant. And there we have this battle of the movement caused by the convection currents and the subduction, the buildup of friction and energy and stress within the rock and its corresponding dynamics and its own characteristics of how it holds and contains stress, and the point of failure where the energy is too great and overpowers the friction, causing the movement and displacement and the corresponding large, powerful earthquake. And each seismic area, each subduction zone has its own characteristics based on the angle, the speed or plate velocity, the rock type, the size of the zone, and also how the energy is stored within the rocks. This all accounts for each region having its own characteristics, and not one is the same as each other across the planet, thus producing different types of earthquakes that are all deemed megathrust. However, there are different time periods and frequencies of each earthquake and how often they occur, and the magnitude of the earthquake and the energy that's released. So these megathrust earthquakes occur on subduction zones around our planet in different tectonic seismic zones, and have produced some of the largest earthquakes ever recorded by mankind. Now, there are 9 principal seismic zones which fall under the characteristics of megathrust. It has the right angle, the subduction zone, and has produced extremely large and powerful mega earthquakes over 9.0 magnitude, which produces insane amounts of energy released from the rock. Now, these zones around the planet are generally oceanic trenches where you have the convergence of the two plates along this subduction zone at a certain angle below 45 degrees, which are the Japan Trench, the Aleutian Trench, the Peru-Chile Trench, the Sumatra and Java Trench, the Cascadia Subduction Zone, which is the Northwest United States and Juan de Fuca Plate Convergence Zone, the Central American Trench, the Kuril-Kamchatka Trench, the Marianas Trench, and the Tonga-Kermadec Trench. Now, as you can see, each one of these 9 principal subduction zone megathrust regions lie around the Pacific Ring of Fire. Out of the top 20 largest earthquakes ever recorded, only one in 1950 in Tibet, an 8.7, has ever occurred outside of the Pacific Ring of Fire. Now, these include the megathrust earthquakes that have occurred, which have been over a 9.0 magnitude rating, which was the Russian Kamchatka earthquake of 1952 at 9.0, the Japanese earthquake of 2011 at 9.1, the Sumatra Indonesian earthquake of 2004 at 9.2, the Alaskan earthquake of 1964 at 9.2, and the biggest ever recorded was the Chile earthquake of 1960 at 9.5. All produced from these subduction zones that are classified based on the angle of subduction as a megathrust seismic zone. In conclusion, megathrust earthquakes are most powerful, most extreme earthquakes ever recorded by humans. They have a high magnitude of over 9.0. They form where convergent plate boundaries occur and ocean trenches form, with the two plates colliding and one plate subducting at a certain angle, less than 45 degrees, and the average is around 30 degrees. And the term derives from the thrust fault, the type of dipsit fault where the hanging wall is forced upwards through compressional stress with large displacement and rupturing, releasing a large amount of energy. Now, these areas around the world pose potential future issues for areas such as the Cascadia subduction zone of northwest states of America, Oregon and Washington and British Columbia in Canada, whereby this subduction zone potentially has a megathrust earthquake in the future, which will pose a threat to the metropolitan areas within that geographical region. And also, in addition to the Cascadia subduction zone, you have the Japan Trench just off the coast of eastern Japan, which is an extremely populated area, with Tokyo being right on the coastline and having millions of people potentially threatened by a future megathrust earthquake, like they experienced in 2011. This is the Earth Science Classroom. Thank you for watching the video. I really appreciate it. And if you get a chance to like and subscribe, that stuff really helps the channel. Thank you so much. And see you again in a future video.